So let's have a conclusion. The dual simplex method helps us to deal with an additional constraint or additional constraints. Okay, they are useful because we sometimes have new resources to allocate, new rules, new regulations, right? So we want to go from our optimal solution, do a few iterations to get to a new optimal solution. Here, we use the dual simplex method, and it has its own pivoting rule, which is a mirror of the prime that in the primal dual. So primal simplex. So the rule is here. For living variable, we look at those basic variables. We choose one that its value is negative, which means we choose a row where the right-hand side is negative. And then we conduct ratio test. We are going to look at all those non-basic columns, and the candidate should have a negative element in the living row. Okay? Otherwise, it's not going to fix the bug at the right-hand side. So once we do this, we're going to check the reduced costs as numerator. So we do all these ratios, we do all this division, and then we take absolute values for all these ratios, and then we see which one has the smallest ratio, the smallest absolute ratio. That one is going to be a non-basic variable, non-basic column that will enter the basis. So this is exactly something that can solve the new constraint problem. The dual simplex method running in this way is going to be a very useful tool for us to deal with this new constraint thing. What's even more interesting in my idea is that it is actually very, very useful when we, for example, do this branch and bound algorithm. You probably know that when we do branch and bound to solve integer programs, each time when we have a problem, when we solve it, and if we get a fractional value, we're going to add constraints to generate new nodes, right? So when we go one step further, we keep adding constraints. And if we go one step further, we need to solve a new linear program in each node, right? If we already solve the linear program that is in the blue box, what's the point of solving the whole, the red one from scratch? You don't need to do that, right? Previously, maybe you say, okay, let's call simplex to solve this. Let's call simplex to solve that. But no, we're not going to do that anymore. We already solved this blue solution and blue variable. I should say, we already solved this blue problem, right? We have an optimal tableau for that blue problem. We have the optimal basis. Then when we need to deal with this red problem, we just add one constraint, and then we run dual simplex, and then we can get to the solution immediately. If we have a branch and bound tree that is very large, if we don't do this incremental thing, if we don't apply dual simplex method, it's going to waste you a lot of time. But luckily, we do have dual simplex that can speed up the whole process of branch and bound in a huge way. So I hope you also agree that dual simplex seems to be very useful, at least if you want to implement branch and bound for integer programs. Okay, so I hope we see that through this lecture, hope you see that we can do sensitivity analysis. We may answer those what if problems. What if we have a new activity? What if we have a new role? And during the whole introduction, we see that maybe duality helps. Duality helps us to invent dual simplex to help us solve this sensitivity problem and help us do better in branch and bound and many other situations. So I hope you like this lecture also. Okay, that's the end. Thank you.